Hi there. If you enjoyed Integration Techniques Part 1, then you've come to the right place for more. This is Integration Techniques Part 2. So in the first problem, they deal you some information about a function called f. First, they give you a graph of f that works between 0 and 5. The only problem with that graph of f is something got spilled on it. So for any x's between 1 and 4, you will notice you can't tell what f outputs. So that's going to create an issue for us. Uh, Further, let's see, they also gave us an equation for the function f that works for x's beyond 5 and beyond. And then finally, they gave us a couple pieces of information about integrals of f over intervals from 0 to 4 and from 4 to 3. By the way, from 4 to 3, those limits of integration are in the wrong order, so we'll have to do something about that when it's time to use those. Okay, so first problem is a fairly typical integration by parts problem. How can I tell it's an integration by parts problem? It's because of the presence of one, two variable containing factors where the derivative of the inside of one cannot produce the other. So we'll have to use integration by parts here. Notice you can contrast that with part B, by the way, which also includes one, two variable containing factors, but on part B, the derivative of the inside of the second factor can produce the first factor. So part B is not going to be an integration by parts problem. So I thought it was important to point both of those out because they look kind of sort of similar in some ways, but they're really different. And for that matter, part C, let's point out, one, two variable containing factors. Is that going to be integration by parts? No, because again, the derivative of the inside of one can produce the other. So A, B, and C all produce two variable containing factors, but only one of them is an integration by parts problem because the other two, the second factor, which is the first one written down, but the simpler factor can be explained from the derivative of the inside of the other factor. So they're both chain rule types of problems, B and C. All right, so let's do the integration by parts problem first. I'll bring it over to this board here. So they want to know what's the integral from 0 to 4 of 2x f prime dx. So remember, we want to call something u and then all the rest is dv. Sometimes it's choosing dv that kind of guides the thought process, and I would say that here. Here it makes sense to call all this dv, the derivative of v, because then v can just be f of x, and we know some information about f of x. Okay, and that would make u this stuff here. So let's go over, write that down, and figure out stuff. Okay, so if dv was f prime, that means that v was f. That would make the derivative of vf prime. If u is 2x, that means the derivative of u is 2 times dx. So let's write things down now. So we need uv, so that's 2x f of x. That part needs to be evaluated from 0 to 4. uv minus integral v du. So that's 2 f of x dx, and that's also evaluated from 0 to 4. If you check it out, this second term, you actually know it. Well, you pretty much know it. You'll have to do just a slight little something, because in the given part of the problem, they said the integral, bring this close to the camera, look at this one right here by my thumb, the integral from 0 to 4 of f is 8. The integral from 0 to 4 of f is 8. And this says the integral from 0 to 4 of 2f. So that's going to be 2, 8. You know, you can bring this 2 out here because it's a constant factor. So what I'm saying is this whole mess here, you don't have to do any more work with. You just have to recognize you've been given it minus 2 times 8 because the integral of f from 0 to 4 was 8. So here, let me make a little room. I'll move that over here. All right, so this part we still have to do, though, which is going to be a plug in, subtract. So plug in 4, that makes 8f of 4. Plug in 0, that makes 0 f of 0. So let's see. Hopefully we can judge f of 4 from the graph, and you can. That's the point 4 comma 3. It's unobscured. So f of 4 is 3. 8 times 3 makes 24 minus. Doesn't matter what f of 0 is. 0 times that will make 0. minus 2/8 is 16. So that's a final answer of 8, all done. Okay, so that was part A. So let's now move on to part B, which at first glance you might think was integration by parts until you take that closer look I took. So it's not integration by parts. That is, the chain rule can explain the presence of that factor x as the derivative of the inside of x squared minus, or the inside of f of x squared minus 1. Derivative of x squared minus 1 makes 2x. I don't mind the 2. I can make that go away, but it creates x. Derivative of x squared makes 2x. So this is just a chain rule situation. Normally we do something like this in our heads. The problem, though, is you don't know what the antiderivative of f is. So you're in a weird spot. Even though you recognize the chain rule should be able to take care of this, you don't know the antiderivative of f. This is going to be a problem where you are forced to use u substitution. Usually I've taught you to just avoid u substitution because you're too smart for it. Like you're going to see in part C, we're able to dodge u substitution, even though we could use it because we're just too smart for it. But in B, you can't dodge it because you don't know the antiderivative of f. Instead, this is sort of a contrived problem to make sure you've seen u substitution, and you're going to put to use one or both of these facts up here. I'm not exactly sure how it's going to turn out yet. So let me show you how it all goes down. And this might be something that you feel a little uncomfortable with because I only showed you u substitution like right at the end of the first semester, and we didn't do much with it. It was just so that I could feel good that I had showed you in case it popped up on your final. Okay. So again, how do you recognize u substitution as the thing? That would be if you see that there's an inside whose derivative is another factor in the integrand. So derivative of that inside is 2x. I don't care about the 2, but x is key. So this came from the derivative of that. That lets me know u substitution can unlock this problem. Again, normally I wouldn't bother with it, but here I'm forced to make something happen. So when you use substitution, the most important thing is establishing what is u. Use the inside. Just that choice of u alone will force 3 of the 4 substitutions. If it's a definite integral, there's going to be a total of 4 substitutions. So let's see how this goes. First, the limits of integration. Those used to be x values. Now they're going to be u values. And how do you find what u values the limits of integration are? We'll just use what u is. If x is 1, then u is 1 squared minus 1, which makes 0. If x is 2, then u is 2 squared minus 1, which makes 3. So, moral of the story. In the x world, it's an integral from 1 to 2. In the u world, the same integral will go from 0 to 3. So there's 2 of the total 4 substitutions that are going to happen. Okay, next I'm just going to copy down the integrand, this part of the integrand before the dx. If it's not something I called u, I leave it just how it is. Like that says x. That's not what I called u, so I leave it just how it is. F of, that's not what I called u, so I leave it just like it is. X squared minus 1, that's what I call u, so I put u in its place. There is the third of 4 substitutions. Limits of integration, change to u's, and then whatever I called u, I substitute with u. Finally, the fourth substitution is one that makes me do work. That is, I can't write dx down here. I can't just copy dx down because the goal is to make this integral only contain u's, no more x's. So I have to replace dx with what dx equals because of my choice of u. So to find that out, I have to take the derivative of my choice of u, call it du dx, and then solve for dx. So I'll multiply dx to the right, and then I'll divide both sides by 2x. Oops, equals dx. So where it said dx, I will replace that. I will substitute in what dx equals, which is du over 2x. And now is when I'll find out if u substitution was going to work for this problem. Of course, I already anticipated it would work. That is, do all the x's go away? Does the magic happen? And yeah, because I get chew. So that brings me to this integral. The integral from 0 to 3 of, you have f of u du, and then you see that divided by 2. That's just like a times 1/2 constant, and I can drag that out to the front. So if there's a way I can know the integral from 0 to 3 of f of something, then I can just take 1/2 of that integral from 0 to 3 of f of something and have my answer. This is where I want to go back to the given information. Now, don't mind that these say x's versus this saying u. It doesn't matter what you call the independent variable. So what I was given is the integral of f from 0 to 4, and then the integral of f from 4 to 3. So let's jot down that information on this board. Integral of f from 0 to 4 is 8. So this, you might remember, I used to make like little number line things for this. So from 0 to 4, over that whole stretch, the integral is 8. Oops. And then they also gave me that the integral of f from 4 to 3, wrong order, of f is -3. What should I do with that? Well, let's change it to the right order. That means the integral of f from 3 to 4. So to reverse the limits of integration, you make opposite. From 3 to 4 is 3. And look what I can now infer. If the integral from 3 to 4 was 3 and from 0 to 4 was 8, can't I figure out that the integral from 0 to 3 must be 5? It's the only way. Yeah, and in fact, now I can drag that back to my problem and I'm pretty much done. So the answer is 1/2 of the integral from 0 to 3 of f, which was 5. So the answer is 5 halves. So that was a pretty slick u substitution problem there. Not easy. Not easy. All right. That's the kind of thing they would have to do to you with u substitution to force you to use it, because you can always dodge u substitution otherwise, for what it's worth. So it's always going to be like this weird contrived thing. Okay, next. I'll just do this one on paper because it's not going to take all that long. So this one says, do the integral of cosine times f prime of sine. Notice this is the same kind of chain rule setup, because the inside of f prime, sine x, its derivative produces cosine. So I know the chain rule explains the presence of these two variable containing factors. So let's get down an antiderivative. The derivative of what would make f prime of sine x? Well, that would be the derivative of f. Derivative of f makes f prime of, leave the inside the same. Don't mess with the inside. By the way, pause and check that your answer is right for the antiderivative. You don't even need any adjustment. Why is the answer right? Because derivative of f of sine x would make f prime of sine x times derivative of the inside, so times cosine x. All right, so we've got f of sine x evaluated from 0 to pi over 2. So that's going to be a plug in, subtract. Okay, sine of pi over 2, that makes 1. Sine of 0 makes 0. Good news, we can figure out both of those from the graph. Coffee wasn't spilled on that part. So f of 1 is 2, f of 0 is 3. So we've got 2 minus 3 makes for a final answer of -1, all done. All right, last problem is going to take a lot of work. It's an improper integral. It's kind of weird because it's an improper integral where they gave you the answer. So they want you to work backwards and try to figure out what something is from the answer. I thought that was sort of a clever problem. It's a way that I could totally see them forcing you to do things on this most unique of AP tests. So let me drag this thing over here and we'll start doing some work with it. All right, so they said something about the integral from a 3 to infinity of f. Now let's pause and take a note. So they told us that equals 9. I'm going to write that way over here. Let's take note though that f between 3 and 5, f is dictated by what's happening in this graph. And then from 5 to forever on, f is dictated by this function here. So we're going to have to break things into parts. We're actually going to need to break things further into 3 parts. I'll explain why I did it afterwards. So I'm going to call the integral from 3 to infinity. Let's call that the integral from 3 to 4 of f. I'm just going to use some shorthand notation here. Plus the integral from 4 to 5 of f. plus the integral from 5 to infinity of f. Where the first two of these we can either just figure out or grab because they gave it to us. All right, so first, integral from 3 to 4, you might remember we knew the integral from 4 to 3 was negative 3, so that makes the integral from 3 to 4 positive 3. Plus, what's the integral of f from 4 to 5? Remember, we have this graph to work with. So from 4 to 5, integral of f would just be the signed area right there. And that I'll leave it to you to figure out that that's a total of 4 for signed area. You can check it out, I promise. And then there's this integral from 5 to infinity that we're actually going to have to deal with. And all that is 9. So I guess moral of the story is, of the 9, that is the total integral from 3 to infinity of f, 7 of that 9 is already covered by the time you get to 5. So that would make the integral from 5 to infinity, which is going to be the one we're working with, 2, as in 3 plus 4 plus 2 would make 9. So we really want to work the problem integral from 5 to infinity of f. Again, why did we need to start that at 5? Because this rule for f didn't start until I get to 5. So let's start working this problem, and we're going to get an answer in terms of a, and then we'll be able to figure out what a is. So we want to do the integral from 5 to infinity of it was 4 divided by x minus a squared. I'm going to immediately rewrite that as 4 times x minus a to the negative 2. That's going to be the key to the antiderivative that we end up doing. Okay, so remember what we have to do. We have to call that instead the limit of a not improper integral. So limit as, normally I use a for my letter, but since a is already in use, I'm going to have to use something like b. So the limit is b goes to infinity of the integral from 5 to b of 4 minus x minus a to the negative 2 dx equals, limit is b goes to infinity of, and the idea is now this integral, that's an a there, sorry. This integral, when I go do it, I'm going to bring back an expression that goes right here. Let me do that integral over here on this other board. I'll erase the other board. I told you this is going to be a really long problem. It's a good problem, but it does take a lot of writing. Okay, so I'm doing the integral from 5 to b of 4 times x minus a to the negative 2. Okay, let's start with an antiderivative. So all that crap to the negative 2 came from taking the derivative of all that same crap to the negative 1. And I just have to adjust for the power rule. The power rule would cause a negative sign, so there used to be a 4 in the front, so now that needs to become a negative 4 in the front. And that's it. There's no baby chain in there because derivative of the inside is 1. So that'll get evaluated from 5 to b. My tip would be, before you evaluate, this is an improper integral, so it's especially important. Any negative powers, undo that earlier rewrite I did, which was to call it a negative power. I like negative powers for doing antiderivatives in calculus often. I don't like them for plugging in. So let's call this negative 4 divided by x minus a to the first. So evaluate from 5 to b. So that's going to make, plug in, subtract, negative 4 over, now I'm plugging in for x, remember, a stays there. So negative 4 over b minus a minus negative 4 over 5 minus a. Okay, so I'm going to take this expression and drag that back to the weighting limit now. The one thing I will do, though, is minus minus makes plus. So you know me, I like to write the positive term first. So let me do that. So minus minus makes plus. That's 4 over 5 minus a. I'll write that first. Minus 4 over b minus a. Okay, so what's this limit going to equal now? Well, notice the first term has no b dependence. That's just going to equal 4 over 5 minus a. It looks weird, but it only looks weird because, remember, the whole problem was weird because it started off with that a. So that was what made this problem so abstract. That's the reason I wanted to do it. Minus. Now, this one does have b dependence. If I plug in infinity for b, first, even though I don't know what a is, given that it's a constant, is that going to mess with infinity? Infinity minus, let's say a is 7. Infinity minus 7, it's still infinity. So what happens when I have 4 cookies divided amongst infinity people? Everybody gets a cookie. So that's a big fat 0 is what that turns into. So that's 4 over 5 minus a. So the value of this integral, in terms of a, it has to be, because I didn't know what a was, is 4 over 5 minus a. Now what I know, remember, is that that integral, I erased it, I guess, but that integral has to be equal to 2. We worked that out earlier. So now I can figure out what a has to equal to make this integral 2. Well, let's see, if 4 divided by something makes 2, then the something down here has to be a 2. So it has to be that 5 minus a is 2. So it looks like that would mean that a has to be 3. So that was a good problem. It was a tough problem, but it was good. I got to say, I really like this whole problem, the whole thing. It's all good stuff. It's really good review. Okay. I'm going to pause for a moment, and then I'll be back with the second problem. Okay, magically I'm back now with the second problem. I saved this for the last integration technique problem we did because it's just so ugly looking. There's so many letters. There's no numbers anywhere. It's just kind of frustrating. So anyway, we'll get rolling on it. We'll do the best we can. I do not plan to do part C. I meant to omit it from the paper altogether. I'll explain why I don't end up doing it other than just the sheer repetitiveness of it. But I will do my best to get through parts A and B. Okay, so we've got this presentation of a function named g that hopefully it looks an awful lot like something that you do partial fraction decomposition to. The only weird thing is that there's this parameter c involved. Well, I guess there's two weird parts. The parameter c involved, but again, that's a way for them to make things more abstract, so you can't kind of just use notes to get by or type things into computer algebra systems to get by. I guess the other weird thing is they make the numerator be called the function whose name is h, so that they can, the only reason they do that is so that they can mess around with what the numerator is. That is, in part C, it's different from what it was in parts A and B. Okay, but for our purposes, since we're only doing A and B, the function we're working with is, because h of x is 6c in both of them, we can just replace h of x with 6c. Note, that would be a constant. You just don't know what the constant is. Now, something to keep in mind is that c is a negative constant for what it's worth. Maybe I'll make reference to that a few times. Okay, so they want us to do an integral for the function g. Hey, there's fraction I'm integrating. Nothing else would work but partial fraction decomposition. So I'm going to be in a partial fraction decomposition world. Again, if those c's were regular constants, I don't think it would be that big of a deal. But that's going to be the gist of the problem, doing a partial fraction decomposition to this. Let me drag it over to my dry erase board, and we'll do our best with it. Okay, so I'm not even writing down the calculus, I'm just writing the fractions. So we've got 6c divided by x plus 2c times x minus c. Okay, so the idea is we want to say how much x plus 2c and how much x minus c are required here to build that fraction. Then remember, we take the whole big mess and hit it with a times both factors, times x plus 2c and times x minus c. And let's see the fallout. So fallout on the left side is both things go choo-choo, and then you're just left with 6c. Now, you might remember in partial fraction decomposition problems, you'll have two types of terms, things that are x containing and things that are not x containing. Don't be fooled by 6c. Even though c is a letter, it's a constant. So that's a constant term. So there's no x containing term here. So I'm going to put, just to remind myself about that phenomenon of the x containing term, I'm going to put 0 x's, just like I always do. Okay, equals. Over to the right side. A is going to get hit with, let's see, x plus 2c's will go choo-choo. So A is going to get hit with the x minus c, plus B, the x minus c's go choo-choo. B will get hit with x plus 2c. Okay, so let me do my distribution, and then I will reshuffle terms. So on the left side, I had 0 x's. Let's see what I've got on the right side, just from the x world. I've got ax plus bx. All right, and then on the left side, I've got 6c in the non-x world, and on the right side, I've got minus ac plus 2bc in the constant, the non-x world. Okay, so now is where you could factor out from the green ones on the right side. You could factor out a common x. And then sort of weirdly, but there's going to be a symmetry to it. From the blue ones over here, you can factor out a common c. All right, and now I can go about my business of doing some algebra. So I know that the coefficients of x on the left and right side have to be the same. So 0 has to equal a plus b. And then I know that the, let's see, that minus sign, I'm sorry, that was kind of bad math I did there. So there's a plus sign, and that negative stays with the a. All right, that's better. And now I've got that negative a6. The coefficient of c on the left side has to equal negative a plus 2b. So let's solve this system. Here I could just add the terms together, and I'll get rid of a. So I've got that b is 2, which means that a is negative 2. Throw those back up here into their right spots, and I can have my partial fraction decomposition now. So negative 2 goes there, and positive 2 goes here. All right, so that was the gist of it. Here, let me come back to the paper and record my findings. That was really the hardest part of the problem, I think, is what we're going to find. So what we want to do is the integral from 4c to 7c of g, where we just decompose g into 2 over x minus c. I always like to write the positive one first. I don't know why I put parentheses there. I didn't need them. It doesn't hurt, but it was just dumb. Sorry. Minus 2 over x plus 2c. And for that matter, I can come down here and fill in the same idea. Here I'm integrating from 1 minus 2c to infinity. Obviously, that's going to be an improper integral, but let me fill in the same decomposition is used in both of them because it's the same function in both. Okay, now here's one thing that's important to check out before I go jumping in too fast with doing an antiderivative. I mean, in some ways the problem's almost done, but in other ways there is a little bit of a possible minefield. So I just have to make sure that I'm good with the idea that I'm not trying to pass through any discontinuities. Note that and I'm not, but I just want to prove it to you. Note that the original function is discontinuous. That means you'll have a vertical asymptote of the way these discontinuities manifest, but discontinuous at, this factor becomes bad at x equals c, and then this one at x equals negative 2c. Now with c being negative, that would mean if I like arrange things on a number line, 0 would be here. Because c is negative, c would be like on the left side of 0, and negative 2c would be on the right side of 0. Negative 2c. So I just need to make sure that I'm not trying to integrate through either of these discontinuities as I do an integral. So let's just think about where these where these limits of integration would be and convince ourselves that indeed we're not trying to integrate through any discontinuities. Okay, so 4c, where would 4c be? If c is negative, 4c is negative, and it's like way more negative. So 1, 2, 3, 4c would be like right here, and 5, 6, 7c would be right there. So it's cool. We're integrating over an interval here that doesn't go through any discontinuities. So that's good. Similarly on this one, let me just justify right now on this one. Let's see, negative 2, 1 minus 2c is equivalent to negative 2c plus 1. So if negative 2c all by itself is there, then negative 2c plus 1 minus 2c would be here, and I'm integrating to infinity. So again, I'm not trying to integrate through either of those discontinuities. That's something in general you just are supposed to check, lest you do something silly and try to integrate through a discontinuity, which itself is an improper integral. So again, we're not doing that. So we can rest assured that that's cool at least. So all I got to do is finish off each of these. The top one's going to be simpler because it's not an improper integral. So really, it's just we can do this one like pretty fast, pretty much. Just antiderivatives. What's the antiderivative of 2 over x minus c? 2 comes along for the ride, and I produce x minus c with natural log of absolute value of x minus c. Minus sign because it says minus sign. Same for 2 over x plus 2c. Same idea. Derivatives of the inside of both of those are 1, by the way, so no need for any adjustment or anything. And then this is going to get evaluated from 4c to 7c. The evaluation might get a little sticky, so why don't I go over to a whiteboard to finish this off? I'm not really sure what to expect. All right, so we were up to here. 2 natural log x minus c minus 2 natural log x plus 2c. And that was evaluated from x equals 4c to x equals 7c. Here we go. So there's going to be a big plug-in with a subtract in the middle. Okay, plug in 7c first. 7c minus c is 6c. So I've got 2 log absolute value of 6c. Oh, you know what we could do? Heck. Look, this part doesn't really matter all that much, no matter what. But I guess before I plug in, why don't I use that property of exponents that says let's factor out the common factor of 2, and then a difference of logs is the same as the log of a quotient. So hold on. So factor out the common 2. Difference of logs is log of a quotient. That's just going to help here. It'll make things as simple as possible. Okay, now we're going to have plug in, subtract. 7c minus c is 6c divided by, plug in 7c here. 7c plus 2c is 9c. And that's going to simplify really nicely in a moment. Okay, now let's plug in 4c. 4c minus 3 is 3c divided by. See, it's no different than normal. Everything just looks like really terribly complicated, you know, because of the presence of these c's. It's just kind of frustrating, I think. I don't know. Maybe you don't think. Okay, so let's see. Why don't I factor out the common factor of 2? And I'm left with, this one gives me the natural log of 6/9, which is 2/3, minus, and this one gives me the natural log of 1/2. Okay, and I could actually do this one more time now. The difference of logs is a log of a quotient. So that would make the log of 2/3 divided by 1/2, which is the log of 2/3 times 2 over 1. That would be the log of 4/3. 2 logs of 4/3. It doesn't matter. I mean, it really doesn't matter how you give the answer. The gist of it was done when we got to here, up here. They're not gonna. There's so many different ways to give answers, and none of them are simpler than any others necessarily. So I wouldn't get hung up on the fine print of the end of the problem. Okay, so let's go to the other one now, and then we will happily be done. And I'll explain to you why I don't want to do C other than the repetitiveness. And I'm sure nobody's watching anymore anyway, and you're banging your head if you are. Okay. So yeah, this is an improper integral. So, I have to go through that improper integral routine of let's replace the infinity with something like a. And we'll do a limit as a goes to infinity of that. So, we'll have to come back and do a limit, but let's first just do the integral itself. So for just the integral itself, again, same antiderivatives. So you're going to have 2 natural log x minus c minus 2 natural log x plus 2c, and that's going to get evaluated from 1 minus 2c to a. You could do the same trick of pulling out the common 2 and calling it the difference of logs the log of a quotient. Okay, so now let's plug in a, and we get log of a minus c divided by log of a plus 2c minus sign. Plug in 1 minus 2c, so let's see, 1 minus 2c minus c would be 1 minus 3c. 1 minus 2c plus 2c would just be 1 down there, unless I mess something up. Okay, and now remember, this has to have applied to it the limit as a goes to infinity. So we want to do limit as a goes to infinity here. Why don't I write down here in this space I'm not going to need anyway. Let's cross out that problem so you don't think I'm doing it. Okay, so now we're going to do limit as a goes to infinity of 2 natural log a minus c over a plus 2c minus 2 natural log 1 minus 3c. Okay, so think about putting infinity in for a. So you get one of these limits that's an infinity over infinity situation. So how are you allowed to think about it? Remember, c is just a constant. So compared to something infinite, c would be negligible by comparison, negligible by comparison. So you could simplify first before plugging in the infinity. A over a approaches just 1. As a becomes infinite, the c's become negligible, and a over a becomes 1. The natural log of 1 is 0. So this first term just becomes 0. And then the answer becomes, well, just the minus the second term part. And that's all done. So, and I don't want you to get too upset about, upset's not the right word, but just too discouraged by these problems here. I thought it was good for me to do something like this for you so you can see it's not impossible. At the same time, they are frustrating. They're really annoying. So, I've got real mixed feelings about them. I liked the first problem a lot better for what it's worth, the coffee stain problem. But, when I think about what the College Board people might do to you with things like partial fractions, it does scare me that you have access to a computer algebra system and notes in a book and everything like that. They might feel the need to make things more obscure. So I thought I should do something like this. By the way, if you care, the reason I didn't do C was they wanted an integral between 0 and -3, and there was no way to know if that was going through a discontinuity. I thought it was a bad problem. With C being negative, what if C were -1? And they want you to integrate between -3 and 0, you're going right through a discontinuity. So it affects things. Whether C is part of the interval that contains a discontinuity or not, it's a problem. So I thought C was a poor problem. That's why I didn't do it. Plus, I think that you've had enough already. It's kind of overkill. All right. Hey, thanks for watching. I appreciate it. Bye.